The future of transportation is being shaped by advancements in robotics and artificial intelligence, with autonomous vehicles leading the charge. In the previous lab, we explored core concepts that directly connect the technologies behind self driving cars. Basic robotic control and kinematics provided insights into how vehicles calculate movements for efficient and precise navigation. Sign recognition uses deep learning, demonstrated how advanced algorithms enable vehicles to identify and respond to road signs and signals, a key feature for maintaining safety on the roads. Path following using imaging processing mirrored how self driving cars stay in their lanes by interpreting roads and markings surroundings. We also studied robot networking and communication, which aligns with vehicle to vehicle and vehicle to infrastructure systems, enabling connected cars to share data and coordinate traffic flow. Position detecting using AprilTag parallels GPS and sensor technologies that autonomous vehicles use to determine their exact location in real time. Finally, path following illustrated how vehicles calculate optimal routes and avoid obstacles dynamically. Together, these concepts reveal the foundations of the technology transforming the way we travel, making transportation safer, more efficient, and fully autonomous. Goal one of this project was to create a flowchart for programming the JetBot to travel from location A to B autonomously using the shortest distance and following the traffic signs. Our flowchart shows the following. First, the system powers on and initializes. It then captures an overhead image of the route. This image is processed to identify key points or nodes along the path. Once the nodes are identified, the system calculates the shortest and most efficient route between the starting point and the destination. Next, the vehicle starts its journey. A camera mounted on the front captures real time images of the road ahead. These images are fed into a deep learning model that can recognize traffic signs like stop and speed limit. Additionally, the model is trained to identify lane markings, particularly yellow lines, which help the vehicle stay centered on the road. If a stop sign is detected, the vehicle immediately halts for a predetermined time. Once the timer expires, the vehicle resumes its journey. If a speed limit sign is detected, the vehicle adjusts its speed accordingly. If no specific sign is detected, the vehicle continues to follow the planned route using its sensors to maintain its course. The system constantly monitors the vehicle's position and adjusts its steering and acceleration as needed to keep the vehicle centered within the lane, following the yellow lines. Finally, when the vehicle reaches its destination, the system shuts down, completing its autonomous journey.
Today I'll be summarizing what we've learned throughout Lab 1 to Lab 3 in our Autonomous Vehicles Lab course. In Lab 1, we were introduced to the JetBot and its basic controls. We explored Python programming in Jupyter notebooks and learned how to operate the JetBot's motors for forward, backward, and rotational movements. We then also had to calibrate the odometry by adjusting the motor biases for straight line motion, and this lab gave us a solid foundation in robot control and kinematics. Moving on to Lab 2, we did two things. First of all, we advanced to path following and sign recognition. Using a camera, we developed a closed-loop control system with a PD controller for path following. This allowed the JetBot to follow a defined path autonomously. Additionally, we utilized transfer learning to train a deep learning model for recognizing road signs like stop and speed. Moving on to Lab 3, we had to tackle more advanced tasks like networking, position detection, and path planning. We used networking to enable communication between the JetBot and a camera bot, which allowed the JetBot to identify its location using captured images. We then calibrated the camera using a checkerboard for accurate measurements. We utilized April tags for real-time position detection and implemented a path planning algorithm to navigate from one location to another location using the shortest route possible. Throughout these labs, we learned a lot of skills like robot control, image processing, deep learning, localization, and path planning. Each lab built upon the previous one, ultimately giving us a strong understanding in how to create an autonomous system.
For our project, we developed a system that combines path following and location tracking to achieve efficient navigation. Path following, which fulfills Objective 3, uses imaging processing techniques to detect and follow a yellow line on the road. This enables the system to stay aligned with the visible path in real time, ensuring consistent movement based on visual input from the camera. For location tracking, which aligns with Objective 5, we utilize a camera mounted above the system to identify and track April tags. This method provides precise positional data, allowing us to determine the system's location at any given time. By incorporating April tags, the system gains reliable tracking capability to enhance its overall performance. By integrating these two components, our project successfully combines Objective 3, path following using image processing, and Objective 5, location tracking using April tags. This synergy enables the system to navigate efficiently while maintaining accurate positional awareness throughout its operation. In summary, the UAV lab provided an opportunity to integrate 6 key learning objectives, each essential for achieving the final goal. First, basic robot control and kinematics lay the foundation for precise movement and orientation, ensuring the UAV could operate smoothly and respond to commands efficiently. Next, sign recognition using deep learning techniques enabled the system to interpret and respond to visual cues, such as reducing speed or stopping based on specific signs, adding an intelligent layer of decision making. The objective of path following using imaging processing techniques allowed the UAV to follow a designated path by detecting visual markers like yellow line on the road, ensuring accurate navigation. This was complemented by robot networking and communication, which facilitated real time data exchange and coordination critical for collaborative or multi system operations. To further enhance navigation, position detection using April tag provided precise location tracking, ensuring the UAV's movements were aligned with its intended path. Finally, path planning enabled the system to anticipate and adapt its route, optimizing its trajectory for efficiently and safety. Combining these objectives over the course of 3 weeks was a challenging yet rewarding experience. The time constraints required efficient teamwork and problem solving, but ultimately we gained a deeper understanding of how to design and implement complex UAV systems. This lab demonstrated the importance of integrating various techniques and how they work together to achieve the end goal of autonomous, intelligent navigation. Through this process, we've enhanced our skills in robotics, communication, and real time decision making, all of which are critical in developing advanced UAV systems for real world applications.